Welcome everyone to 11.1 sequences. Now in this section we're going to go ahead and examine some properties of sequences and their limits, and then we're going to use limits of functions, which we already have a good base on from Calc 1 and then also Chapter 6 here in Calc 2, and that's going to help us calculate out some limits of sequences. Alright, so let's get to it with a definition. So the first thing I should probably tell you is, what is a sequence? A sequence can be thought of a list of numbers written in a definite order. All right, so let's choose some real numbers here. A1, A2, A3, and we'll keep on going. A4, dot, 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 all the way to AN and beyond. So A1 is a real number, and it's called the first term. A2 would be the second term. And in general, AN, or sometimes you pronounce this A sub n, is going to be the nth term. All right, now there's other ways that we can denote sequences. First of all, sometimes you'll see them with braces around it, so I'll go ahead and put some braces up here. So some other ways we can denote sequences is just as A sub n with braces around it, or you may want to specify where you're starting and ending. So braces around AN, and then starting at n equals 1 and finishing at infinity. So it keeps on going forever. All right, why don't we try an example here? I want to try to write a function with a domain z positive that defines the following list of numbers: 12, 14, 16, 18. So the first thing, what is this z positive or z plus? Well, this is just the positive integers. So like 1, 2, 3, 4, and it keeps on going on forever. Okay, so a function, here's the outputs. And so the idea is when I plug in 1, I would like to get out 12. If I plugged in 2, I'd like to get out 14. If I plugged in 3, I'd like to get out 16, and 4 to get 18, and so on. Okay, so remember here I'm trying to write a function that gives me out these values. So I have to think about, the different types of functions that I know, and this one looks awfully linear to me because this difference between each term is 2. So I think I'm going to try to make a linear function. So in that case, because this difference is always 2, we would know that the slope of my function would have to be 2. So 2n and then plus something. So remember, when I plug in 1, I need to get out 12. So n would be 1. I need to get out 12, so this is going to be plus 10. Okay, well that works for the first one. What about for the second one? If I plugged in 2, would I get out 14? Yes. How about 3, 16? Yes. 4, 18? Perfect. So if you wanted to, you could also write this as a sequence, right? So the sequence, the nth term of the sequence would be this 2n plus 10. So by writing it as a function, you're also finding this nth term of the sequence. Okay, now whenever you have an infinite list of numbers like this, there's kind of a natural, interesting question. And so this is kind of what this definition is. We can talk about a sequence's limit. So a sequence has a limit L, then we write the limit as n approaches infinity of a sub n is equal to L, or if you'd like, you can write this an approaches L as n approaches infinity. All right, so this has a limit L if we can make the terms a sub n as close to L as we'd like by taking n to be sufficiently large. So if this limit exists, well then we say that the sequence converges. Or another way to say that is convergent. Otherwise, we say that the sequence diverges or is divergent. All right, now let's take a look at this nice big theorem here. We're going to be talking about a function f of x, and suppose it has a limit L, and that an, our sequence, is defined as f of n, where n is of course an integer. Then the limit as n approaches infinity of our sequence, right? So just our sequence here will also converge, and it will converge to the same limit L. Okay. So theorem 11.1.5 implies that many of the properties of limits of functions apply to limits of sequences. So we're using limits of functions to say something about limits of sequences. So for instance, this next theorem that talks about if you have two sequences, one approaches L and one approaches M, then if you take the limit of the sum of those sequences, well, you would get exactly what you would expect, L plus M. Now likewise with the product, right? A sub n times B sub n will be, well, L times M. And then finally, we could write down like a squeeze theorem for sequences, right? So if A sub n is less than or equal to B sub n, and B sub n is less than or equal to C sub n for some n greater than n naught, whew, and the small term and the big term approach L, so that is, A sub n and C sub n, these both approach L, well then the middle term, this B sub n, this middle sequence, also approaches L. All right, one final theorem. This sometimes comes in useful. If the absolute value of a sequence approaches 0, then the sequence itself approaches 0. Okay, so there are many more theorems out there for functions, and therefore they can be applied for sequences, but let's try to do an example here. So I have this function, or you can think of it as a sequence, this cosine of n over n, and I think we're going to want to apply the squeeze theorem here. So let's go ahead and write out really quick what the sequence looks like. It would be cosine of 1 over 1, cosine of 2 over 2, cosine of 3 over 3. And the question is, if this goes on forever, does it actually approach something? And well, the big thing we need to use, hopefully you remember back from maybe Calc 1, is that cosine and sine are both bounded between -1 and 1. And this gives us a very natural way to set up using the squeeze theorem. Now we could go ahead and divide through by n on all sides. Now remember, n is a positive integer, so you don't have to worry about flipping the inequalities or anything like that. And we know that the big sequence and the small sequence, so -1 over n and 1 over n, they both approach 0, right? As n gets very, very large, this thing gets closer and closer to 0. So therefore, the sequence in the middle, by the squeeze theorem, also must approach 0. All right, and there we go. So that's how we can apply our new squeeze theorem for sequences. All right, now let's go ahead and look at one last remark here. So we have the sequence r to the n power is convergent if r is between -1 and 1, we can include 1, and divergent for all other values of r. So let's go ahead and just write out this r to the n power, right? This would be the sequence r to the first, r squared, r to the third, r to the fourth, r to the fifth, so on and so forth, forever and ever and ever. And so the question becomes, when will this actually approach some finite real number, right? And the claim is, well, if r is between -1 and +1, this will actually head towards something. So why don't we go ahead and pull out our calculator really quick. And let me go ahead and clear the screen here. And let's go ahead and see. We'll choose a random number between -1 and 1. I guess 0.73 I'll go ahead and choose. And let's see what happens when we start raising this to larger and larger powers. The claim is that it should actually approach some finite real number. So here's 0.73 to the fourth, and 0.73, let's do to the 100th. Ooh, look at that. That's got an e to the -14, so that's 13 zeros, and then this number here. What about if I raised it to the 1000th? Wow. E to the -137, so that's 136 zeros, and then this number here. So this seems to be approaching 0. As n gets larger and larger and larger, this is becoming very, very small. It stays positive. And you can see even with negative numbers. So here's a nice random negative number. Oh, wow. So I rose it to a power so high that the calculator cannot tell the difference between the result and 0. So this number actually isn't 0, but the calculator can't tell the difference. So in general, if you have r between -1 and 1, and you're not including 1, this limit approaches 0. Now if r is equal to 1, and you take 1 and you raise it to larger and larger powers, well, take your favorite power, raise 1 to that, and yeah, well, you take 1 and you raise it to really any power, it's going to be 1. So this is what it converges to. And you can see it converges to different things depending on what r is. Now, if you take a value that's slightly bigger than 1, let's go ahead and we raise that to larger and larger powers. There's 1.01 raised to the third power. Why don't we go ahead and take that, raise it to the 10th power. Okay, 1.1. How about the 100th power? Okay, it's getting a little bit bigger now. How about the 1000th power? Oh, wow, there we go. Now this is finally starting to climb a little bit. How about, yes, 10,000th power. Now you can see there's an e to the 42, so this is becoming a very, very large number. Okay, and with that, I think we'll go ahead and take a break and stretch our legs. When we come back, we will talk about increasing and decreasing sequences, along with a few more examples. So, I'll see you shortly.